Hey guys, welcome to the fourth episode of Short Bits by Shorty. There were no constructive feedback last time, just a lot of funny ones, and I actually laughed out loud. Y'all know how my laugh is. Anyway, so let's get started. Okay, so just go over the basics. The ribosome, or the bacterial ribosome, is composed of a 50S and a 30S subunit, where the 50S subunit is bigger than the 30S subunit. Remember that the chemistry of the translation, or where the peptide bonds and ribosomes in translation are happening in the 50S subunit. So the chemistry happens, or the peptide bonds happen in the 50S subunit, and the decoding or the matching of the proper anticodon in the tRNA to the codon in the mRNA happens in the 30S subunit. Remember, there's an exit site. Oh, forgot to label that. There's an exit site right here. Oh, whatever. This is the exit site right here, where the growing peptide, the growing polypeptide, the growing peptide chain comes out in the exit or the E site. The peptide elongates in the P site, and it enters the ribosome in the A site. This is the mRNA strand in white. So, the mRNA comes in through the A site, it grows in the P site of the 30S subunit, and it exits at the 50S subunit side. And remember that the chemistry or the peptide bond formation happens in the 50S subunit side, and the decoding or the matching of codons to the anticodons happens in the 30S subunit side. So, how do drugs selectively target bacteria instead of humans? Well, bacteria have different subunits in the ribosome compared to humans. So bacteria have a total of a 70S ribosome, which is composed of the 50S subunit and the 30S subunit. And inside the 30S subunit is the 16S subunit where most of the drug action happens. In humans, it has a total of an 80S ribosome, which is composed of a 60S subunit and a 40S subunit. The way I remember this is that humans have 10 more S's than bacteria. So 70S plus 10S gives you 80S, 50S plus 10S gives you 60S, and 30S plus 10S gives you 40S. So if you remember bacteria, just add 10 to every number and you get the subunits for the humans. Okay, so first we're going to talk about the structure of aminoglycosides. So aminoglycosides have the common pharmacophore of the 2-deoxystreptamine. Say it with me now, 2-deoxystreptamine. Alright, so the common pharmacophore of aminoglycosides is 2-deoxystreptamine right here. And it looks like a sugar, 6-carbon ring with some oxygens attached, looks like a sugar. And it has amines because it's, what do you call it? 2-deoxystreptamine. So look for the the sugar-looking molecule with amines, and that's the common pharmacophore, the 2-deoxystreptamine. Say it one more time, 2-deoxystreptamine. Say it in your sleep. Alright, so there's two drugs that Dr. Ellis highlighted. There's amikacin and there's neomycin. He highlighted these because amikacin is pretty resistant. I'll talk about it later because of the presence of this little tail at the end. So if you see an aminoglycoside with a tail, it's probably amikacin. Neomycin, he highlighted it because of the ribose ring right here. It's a 5-carbon ring that looks like 5-carbon ring with oxygens, and it's a ribose ring. So, when you're differentiating between amikacin and neomycin B, look out for the ribose ring, the 5-carbon sugar-ish ring, and neomycin B, and the tail-looking thing in amikacin. And always look for the common pharmacophore, which is 2-deoxystreptamine. So you have 2-deoxystreptamine right here, in amikacin and 2-deoxystreptamine right here in neomycin B. So know that pharmacophore, say it in your sleep, look at it in your sleep, and you should be fine. Okay, so Dr. Ellis wanted to highlight this. Aminoglycosides are mostly natural products, and you know that natural products are mostly mixtures. However, he highlighted two of them. He highlighted amikacin and tobramycin. So amikacin is prepared from kanamycin, so it's a semi-synthetic product. So it's made half from the natural product, which is kanamycin A, and then they synthesize it in the lab to make, or they change it around in the lab to make amikacin. Tobramycin is made via fermentation, so it's not made totally naturally. So the way that aminoglycosides work is that they bind to the 16S subunit of the subunit of the 30S subunit of the bacterial ribosome. So here is the 30S subunit of the bacterial ribosome close up, and I highlighted the 16S subunit where the aminoglycoside in white binds. So first they bind to the 16S subunit. Then this causes mistranslation. So this causes the wrong protein to be formed because the wrong amino acids or the wrong codons are being matched to the wrong anticodons. So wrong amino acids are formed, and this leads to membrane disruption because amino acids can form the membranes, and if you can't form the membranes right, if you can't form the amino acids right, then you can't form the membranes right, then you disrupt the membrane. So when the membranes are disrupted, then more aminoglycoside enters the cell, and then this whole process keeps going where mistranslation keeps happening, and the bacteria can't make the right proteins for anything, and this eventually leads to bacterial death. So basically, a low concentration of aminoglycoside causes membrane disruption, which increases the concentration of aminoglycosides because of membrane disruption, and this increased concentration causes cell death. So a low concentration initially starts with the aminoglycosides, and then they build up to make a high concentration in the bacterial cell to cause cell death. Okay, so there's three different resistance mechanisms that bacteria have developed against aminoglycosides. There's enzyme-mediated chemical modification, there's modification of the drug binding site, and there's efflux bumps. So I'll go through each one. First, enzyme-mediated chemical modification. So if you modify the drug, if you add different groups to the drug, you decrease the binding because this disrupts the hydrogen bonding that the drug makes with the different amino acids in the ribosome. So to illustrate, oh man, I hate this. Oh man, okay. So to illustrate, we're gonna look at amikacin first. We're just gonna look at amikacin. So amikacin, remember that hydrogen bonds happen when there's a hydrogen bond donor and a hydrogen bond acceptor. So let's look at the hydrogen bond donors in amikacin. So here's amikacin. Why is this amikacin? Because remember, it has a common pharmacophore. It has the common pharmacophore, which is 2-deoxystreptamine, which is right here. And look for the little tail at the end, and you know it's amikacin. So here's a hydrogen bond donor because it has an oxygen with a hydrogen, so it can donate a hydrogen to form a hydrogen bond. Same way, here's an oxygen with a hydrogen, amine with a hydrogen, oxygen with a hydrogen, amine with a hydrogen. There's a lot, just to illustrate a few. So those are your hydrogen bond donors. And these form hydrogen bonds with different amino acids in the ribosome that accept these hydrogen bonds. So basically, amikacin forms hydrogen bonds within the ribosome. And this keeps amikacin binding in the ribosome because different bonds, the hydrogen bonds help amikacin to bind within the protein. So if you take away these hydrogen bonds, you take away these different bindings, and you take away the binding of amikacin or aminoglycosides to the ribosome. So there's different ways that bacteria have taken away these hydrogen bonds. So they can either, one, acylate the NH2, phosphorylate the OH, and adenylate the OH. So, test type of question. If I show you amikacin, show me one part of the molecule that you can phosphorylate. So, remember that phosphorylation happens at OH. So you can either phosphorylate here, I don't know, here, 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 here. Look for the OHs and you can phosphorylate them. Question 2. Show me part of the molecule that you can acylate. And if you don't know what acylate means, let me show you. You know what phosphorylation is. I'll just draw them out for you, whatever. Acylation is adding an acyl, or basically a ketone group. Phosphorylation is adding a phosphate group. And adenylation is adding an adenosine group. Don't feel like drawing that because that's pretty big. So, back to question 2. What's one part of the molecule of amikacin that you can acylate? Remember that acylation happens at NH2 groups. So you can only acylate, I don't know, this one, this NH2, this amine. That's not an amine, that's an amide. So you can acylate this one, and this one. Not this one right here, because it's an amide, not an amine. Oh, you can acylate this one too, on the bottom. Okay, question 3. What are some parts of amikacin that you can adenylate? Remember that you can only adenylate OHs. So, just like phosphorylation, you can phosphorylate OHs. You can also adenylate OHs. So, here's an OH. You can adenylate or phosphorylate. You can adenylate or phosphorylate this OH. You can adenylate or phosphorylate this OH. And so on and so forth. Hopefully you get the point. If not, let me know and I'll clarify it again for you. Okay. Another way you can, or bacteria have developed resistance to aminoglycosides is by modifying the drug binding site. So bacteria have methylated or add methyl groups to the ribosomal binding site, the 16S subunit binding site, so that aminoglycosides can't fit, because if you add a methyl group, you push aminoglycosides out, and they can't fit into the binding sites anymore. So bacteria have modified the drug binding sites by pushing aminoglycosides out by the addition of methyl groups. And of course, bacteria have developed efflux pumps. So they pump the aminoglycosides out of the cell. So, Dr. Ellis wanted to highlight that enzyme-mediated modification is not good with amikacin, and methylation of the drug binding site is not good with neomycin B. So, if you have bacteria that are resistant because they have developed enzyme-mediated chemical modification, you can use amikacin with them, because amikacin is not affected by enzyme-mediated chemical modification. And I'll go back to amikacin because I said I would earlier. So apparently, this little tail end of amikacin makes the molecule resistant against enzyme-mediated chemical modification. So, if you have bacteria that phosphorylate the OHs, or adenylate the OHs, or acylate the NH2s, then you can use amikacin, because this little tail end prevents phosphorylation, adenylation, or acylation. If you have bacteria that are resistant because they methylate the binding site, then you can use neomycin B. So neomycin B is not affected by methylation of the drug binding site by bacteria. So amikacin is not affected by enzyme-mediated chemical modification, and neomycin B is not affected by methylation of the drug binding site. Oh wait, last thing about aminoglycosides that Dr. Ellis wanted to highlight. If you mix aminoglycosides and beta-lactams together, you can form an inactive drug or an inactive beta-lactam, because the beta-lactam can ring open, or the aminoglycosides can open up the beta-lactam ring, as shown here. So you have a stable beta-lactam ring here, aminoglycoside pops in and opens up the ring, and you have an inactive drug. Oh wait, so next class of drugs that Dr. Ellis talked about are the tetracyclines. So I'm not going to draw all the tetracyclines, but one I want to highlight is tigacycline. Technically isn't a tetracycline, it's actually a glycycline, but it's a kissing cousin according to Dr. McRae, so they're basically the same. I wanted to highlight that you can figure out it's a tetracycline because it has 4 cyclic rings over here. So tetra meaning 4, cyclines means 4 cyclic rings. So look for 4 cyclic rings and you get a tetracycline. Easy to remember, hopefully. Just like amikacin, this tail end at the end of the molecule helps the drug act against resistant bacteria. So just like amikacin, the tail end helps the drug act against resistant bacteria. Okay, so there's 3 pKa's that Dr. Ellis wanted us to know in tetracycline. There's pKa 1, which occurs in the bottom right of the molecule, which is at 3.3. pKa 2 is at 7.7 at the bottom left of the molecule, and pKa 3 is pKa 3 is 9.5 at the top of the molecule. Yeah, 9.5. So you can, way to remember this is it's like a little clock. So 5 o'clock you wake up at pKa 1 at 3.3. We used yellow. Wake up at 3 o'clock with pKa 1. Ooh, it's 7 o'clock with pKa 2. You get it? 7 o'clock, 7.7. And I don't know, 9 o'clock-ish, you might brush your teeth with pKa 3 at 9.5. So yeah, think of it as a little clock. So wake up at 3. Ooh, man, wake up at 3 for pKa 1. I don't know what you do at 7 o'clock. You do you. At pKa 2 at 7.7. 7 o'clock for 7.7. pKa 1 is at the 3 o'clock. So the right side of the clock is at 3. pKa 3.3 is at the right. Moving along the clock, 7.7. Look, it's at 7 o'clock-ish. Then 9 o'clock, if you turn your head around, close one eye, close the other eye, get to the top, and you're at 9 o'clock. And with pKa 3 at 9.5. Oh, that's one way to remember it. So, at each pKa, there's something different that happens with the molecule. So let's start with pKa 1. So at pKa 1, you epimerize, or you flip the stereocenter if the pKa gets below 3.3. So, which is the pKa of this first functional group-ish. So if you get less than pKa 1, So if you get less than 3.3, you epimerize, or you flip the stereocenter of carbon 4, which is this carbon right over here. What is happening? Right here in the blue. So if you, I'll do it red since I'm doing PK1. PK2 is blue. So the nitrogen, the bond with the nitrogen over here flips from a wedge to a dash. That's right. So at pH is less than 3.3, the bond between carbon and nitrogen over here flips from a wedge to a bond at pH is less than 3.3. That's called epimerization. And this results in an inactive drug. Now let's go 7 o'clock. You have pKa2. At 7 o'clock, you lose the hydroxyls at physiological pH. So these hydroxyls, these hydrogens are lost at pH 7.7 at physiological pH. And this results in two consequences. One, you can form salts, form insoluble salts. With iron 2, calcium 2, and magnesium 2, and aluminum 3. You can either remember the numbers as these are the charges, regular charges of ions. So calcium usually forms a 2+ charge. Magnesium usually forms a 2+ charge. Iron, you can form 2 or 3+ charges, but here iron chelates or forms an insoluble salt with the tetracyclines at the +2 charge. And aluminum usually has a +3 charge. Another way you can remember it is, that's a 3. Another way you can remember it as Fe-Cam2 and aluminum 3. So Fe-Cam2 has a 2+ charge. Fe-Cam, say it enough times it sounds like a real word. Fe-Cam2, and aluminum 3. So those are the salts that tetracyclines form at pKa 7.7 because you lose a hydroxyl over here. You lose the hydrogens over here. And this is important because if you give your patients calcium supplements, magnesium supplements, aluminum or iron supplements, you would want, or antacids, or dairy products, you would want to avoid giving these within a few hours of each other so that you don't form these insoluble salts. Another consequence is that it works within the MOA to have the hydrogens taken off. I'll show you guys later. So taking off the hydrogens is important because it works in the mechanism of action. Now for 9 o'clock at the top, when you turn your head, close one eye, close the other eye, and it's 9 o'clock at the top, not at the left side like it should be. So if at pKa3, which is at 9.5, you are greater than the pH, physiological pH, so that means you protonate the amine. And this is important for the MOA also. So just to go over what I just said, tetracyclines at 3 o'clock, pKa 3.3, you epimerize if you go lower than, if the pH is lower than 3.3, which forms an inactive drug. 7 o'clock, pKa2 at 7.7, you form insoluble salts, and you also help with the mechanism of action. And remember, don't administer dairy products, antacids, or multivitamins within a few hours of tetracyclines because they can form insoluble salts. At 9 o'clock, you protonate the amine, and you get the mechanism of action, which I will show right now. Okay, so I just drew the core structure of the tetracyclines. Didn't want, too lazy to draw the full structure with all the atoms and everything. Just wanted to highlight everything involved in the mechanism of action. So remember that pKa2, 7 o'clock, 7.7, is involved in chelation of metals. And one important metal in cells is magnesium. So remember, magnesium has a 2+ charge, just like I said. Fecam2. Say it enough times, it sounds like a word. Fecam2. Magnesium has a 2+ charge. Since magnesium has a 2+ charge, you want to balance out the charges in the cell. So you're going to form, here's a negative charge, which balances out one positive charge. The negative charge balances the second positive charge to completely balance out the two charges in magnesium. And you just have the random oxygen that magnesium binds over here. So remember, magnesium binds to two negative charges to balance out the two positive charges through two phosphates. And then a random oxygen over here. So like a random side chick. And then at pKa3 at 9 o'clock-ish, remember that charges have to balance out in the cell with a random side chick sometimes. So you have a negative charge balancing out the positive charge and the amine, the one positive charge of the amine, and that's all you need. So that's the way the mechanism of action works for tetracycline. It binds to the 16S ribosomal subunit. That's important. So tetracyclines bind to the 16S ribosomal subunit, just like aminoglycosides, and by binding to this, by binding to the 16S ribosomal subunit, they cause mistranslation, which causes membrane disruption, which increases the concentration of tetracyclines in the cell, which further disrupts the membrane and the cell, and disrupts amino acid translation, and cause bacteria to die. And they bind to the 16S ribosomal subunit by binding to different phosphate groups and different side chicks like oxygen. Okay, so there's 3 important reactions that tetracyclines can undergo that can make them inactive, ineffective, or just bad. One is dehydration, which inactivates the drug. And you can see this because the drug looks like a deeper color in the bottle. And this does not happen for aminocycline and doxycycline. A second reaction that can happen is epimerization. You know what epimerization is. It's when the stereocenter changes. So from wedge to dash or dash to wedge. Cool thing that happens, so when you dehydrate a tetracycline and when you epimerize it, you get a renally toxic compound. Again, this does not happen for aminocycline and doxycycline. Third reaction that can happen is cleavage, or one of the rings in the tetracycline ring group. So one of the rings in tetracyclines opens up when the pH is greater than 8.5. So know these 3 different reactions. You might be testing on them. Last thing about second to last thing. Dr. Ellis highlighted this. Where's my glycycline? Oh yeah, here's my glycycline, tetracycline. So, the reason tetracycline is resistant or increasingly resistant against resistant bacteria, or why tetracycline works against resistant bacteria, is because this little tail end right here makes additional contacts with the ribosome to increase binding. So this ring, no, it'll be red. This little tail over here increases contact with the ribosome, which increases the binding of tetracycline and allows it to work effectively in resistant bacteria. Remember that it binds to the 16S subunit of the ribosome. And speaking of resistance, here are some resistance mechanisms that bacteria have developed to work against tetracycline. So speaking of resistance, bacteria have developed at least 2 ways to become resistant against tetracyclines. One is decreased accumulation, and 2 is decreased binding site access. So number 1, bacteria have either decreased the influx of tetracyclines, or they have pumped out or effluxed tetracyclines in an energy-dependent manner. So they use, ATP. So it's energy dependent, remember that. Number 2, they have decreased binding site access of the tetracyclines to the 16S subunit binding site. And they do this by displacing tetracycline by a bacterial protein. So bacterial protein comes into the 16S subunit, displaces tetracyclines, and they can't bind any longer and act. Now we're going to talk about the Mls drugs, which all act at, I think, the same subunit, the 50S subunit, instead of the 30S subunit like aminoglycosides and tetracyclines. So, Dr. Ellis talked about resistance to these drugs first. Oh, by the way, MLS stands for Macrolides, Lincosamides, and Streptogramins. Or the way you can remember this is this test Major League sucks. MLS Major League sucks because it's after spring break. And these drugs all act on the same subunit, 50S. And you can group them together. 50S subunit drugs are MLS, Macrolides, Lincosamides, and Streptogramins. Major League sucks, MLS, because it's right. This test is right after spring break. So, these drugs are resistant in bacteria because bacteria have produced an ERM gene, which produces the ERM protein. And this protein converts adenosine in the ribosome to dimethyladenosine. So basically, this protein, the ERM protein, methylates adenosine to produce dimethyladenosine. And what do you do if you add groups or add more blocking groups in a ribosome? You push the drugs out because there's less space for the drugs to fit because of the dimethyladenosine. The extra methyl groups push the drugs out of the 50S subunit and they can't act any longer. Okay, so here is one macrolide. We're just going to talk about one structure-activity relationship of the macrolide, and that's erythromycin. Remember, macrolides have a large ring over here. That's why they're called macro, because there's a large ring. And you have lactone over here. So always look for the large ring with the lactone, and you have a macrolide. There's two important rings attached to the macrolide. There's this osamine ring at the top, and there's cladanose ring at the bottom. Way you can remember this is that, well, this osamine is at the top, cladanose is at the bottom, or you can remember that this amine has an amine over here, and cladanose does not have amine in the ring, and there's no amine in the ring. That's one way to remember it. And these sugars are here because they lead to antibacterial activity. So there's two semisynthetic analogs within the macrolide class. There's azithromycin and clarithromycin. I wouldn't know anything about that other than there's two semisynthetic analogs. There's azithromycin and clarithromycin. So the way that macrolides work is that they bind to the 23S subunit and the 50S subunit. And this 23S happens to be the exit tunnel, like I showed you guys at the beginning of the video. And if you block the exit tunnel, you block polypeptides from leaving the ribosome, and you block proteins from acting in the bacteria. And if you stop proteins in the bacteria, you kill the bacteria. And it just so happens that the cladanose ring and this osamine ring, like I showed you earlier, over here, are important for inhibition activity. Meaning that they help block the exit tunnel in the 23S subunit of the 50S subunit. So remember that this osamine and the cladanose ring are both important in inhibition activity. If you take them out, you can't inhibit the ribosome and the bacteria survive. Another cool thing about this structure is that remember earlier when we protonated, the amine over here, and this interacted with the ribosome by a phosphate group. In the same way, if you protonate the amine, check, did I mess something up? Nope. If you protonate the amine in your macrolide, you get the same binding in the ribosome. So if you protonate this amine right here, you form a positive charge, and to balance out this positive charge in the cell, you bind to a phosphate group in the ribosome, and that gets you to bind to the ribosome. Nice. And remember that both these rings, the cladanose ring and this osamine ring, both are important for inhibition activity. So there's three different resistance mechanisms that bacteria have developed. There's the one, which is which we talked about earlier. There's active efflux. They use energy-dependent effluxing or pumping of the macrolides out of the cell. And there's hydrolysis of ester by esterases, which happens in the Enterobacter family? Genus? Family? I don't know. Anyways, so look at the ester right here. You know that this is broken down by esterases in Enterobacter. This is called the lactone ring, which is a type of ester. It's a cyclized ester. So since there's an ester, you can hydrolyze it by esterases, and this happens in the Enterobacter family. So lincosamides include clindamycin and lincomycin. You can tell it's a lincosamide because there's an amide that's linking the other parts of the molecule. So link amide. So the amide in the middle, links the left side and the right side of the molecule together. So look for the amide that's linking the left side and the right side of the molecule together. Apparently, the chlorine And clindamycin increases your lipophilicity and your absorption. Can't spell today. So the chlorine increases your lipophilicity and your absorption. And there's two prodrugs to clindamycin that modulate their solubility and their permeability and hence their absorption. So there is clindamycin phosphate and there's clindamycin palmitate. These are both prodrugs, and they increase the solubility of clindamycin in the body, which increases their lipophilicity, which increases their absorption in the body. So, last family of drugs in the MLS Major League Sucks triad. There's a streptogramins. There is dalfapristin. I'm not going to draw the structures because I don't think he highlighted them. And they're pretty big and I don't feel like drawing them. And don't think we'll be testing on them because they're pretty big and hard to put an SAR to them. So there's dalfapristin and there's quinipristin. And these are formed in a 70-30 mixture to form Sinercid. Oh, forgot to tell you, or forgot to remind you. Remember, Mls drugs bind to the 50S subunit of the ribosome. Clindamycin, or the lincosamides, bind to the same binding site. Well, no, hold on. They overlap. Lincosamides overlap binding sites with the macrolides, but they are not identical binding sites. So they bind to the exit tunnel, but not at the same place in the exit tunnel as the macrolides. So they overlap binding sites, but not identical binding sites. In the 50S sub 23S subunit of the 50S subunit of the ribosome. Streptogramins also bind to the 23S. Man. 23S subunit in the exit tunnel, basically. These both bind to the exit tunnel and prevent the polypeptide from growing out of the ribosome and prevent amino or proteins from acting in the bacteria, and that's called cell death. Before I go on, quinipristin binds deeper in the exit tunnel. And dalfapristin binds at the beginning of the tunnel. And together they act synergistically. So this is a synergistic interaction. Now moving on to resistance mechanisms. Okay, so dalfapristin and quinipristin each have their own resistance mechanisms in bacteria. So in dalfapristin, bacteria have acylated an OH group in dalfapristin, and they use a CFR enzyme, not the enzyme. They use a CFR enzyme, like you'll see later with the linazolid, and this methylates some group in the ribosome. Just like methylates, CFR methylates, but CFR is used in dalfapristin and the linazolid. Quinipristin acts the same as the other Mls drugs because they use So remember, dalfapristin and quinipristin have different resistance mechanisms. but they all end up with the same result: resistance against these drugs. So, oxazolidinones include linezolid and tadazolid. You can tell it's an oxazolidinone because you have an ox-azole ring. So, ox corresponds to the oxygen. Azo refers to an N with an O. Azo pretty much means N, nitrogen. So, ox-azole means you have an oxygen and a nitrogen ring. Oxazole ring is an oxygen and nitrogen ring together. So you can tell it's an oxazolidinone because it has an oxygen and nitrogen ring. Plus, it's a pretty small molecule compared to the other ones. And these work by binding to the 23S subunit in the 50S subunit, specifically the A site of the ribosome. So while the other drugs act in the exit tunnel, this one, oxazolidinones, act in the A site, but they all act in the 23S subunit and the 50S subunit of the ribosome, which is why they were grouped together in this lecture. Okay, so two resistance mechanisms the bacteria have developed against the linezolid and tadazolid, which are oxazolidinones, and they're called, remember, oxazolidinones because you have an oxazole ring, which is the ox-azole ring over here. Okay, they developed resistance against oxazolidinones by efflux pumps and CFR methylation. Remember that dalfapristine also uses CFR methylation, and what this is that the CFR enzyme methylates the 23S subunit. And what happens when you add a methyl group or you methylate a binding site? You push the drug out and it can't work anymore because the drug can't fit because of the extra methyl groups. And here is a little table I made with all the resistance mechanisms and each drug class for this video. I'm not going to go over it since I already went over it earlier, just putting everything into one table. Now for the fun part, I get to review everything in 2 minutes or less. Okay, let's go back to the top. Oh, wow, this is a long video. Because it's a long lecture. Oh man. Okay, cool, we can play that game. Almost there. Cool. Okay, so the ribosome is made up of the 50S subunit in bacteria and 30S subunit in 30S subunit. Remember, there's an exit tunnel where the growing polypeptide leaves, and there's an A site, P site, and E site. Bacteria and humans are different because humans have 10 plus 10 subunit difference in bacteria. Aminoglycosides work, and tetracyclines work by binding to the 16S subunit of the 30S subunit of the ribosomes. Remember that aminoglycosides have the, what do you call it, common pharmacophore? Gotta say in your sleep, 2-deoxystreptamine. Remember, amikacin is an aminoglycoside that has a tail end, and this tail end helps it against resistant bacteria. Neomycin B has a ribose ring, and that helps differentiate against amikacin. Kanamycin A is used to produce amikacin, and tobramycin is made by fermentation. Already gave you the mechanism. Binding to the 16S subunit allows for mistranslation and membrane disruption, and allows more aminoglycosides to enter the cell, which continues the cycle and causes bacterial death. Here are some different resistance mechanisms. Remember that enzyme-mediated chemical modification is not useful for amikacin, and methylation of binding site is not useful for neomycin B. Remember that aminoglycosides and beta-lactams can interact to open the beta-lactam ring. Tetracyclines work the same way as aminoglycosides by binding to the 16S subunit. Remember, tetracyclines have tetracyclines, so 4 cycles, 4 rings. Tetracycline has this little tail end, just like amikacin, and this increases the contact with the ribosome, which increases binding in the 16S subunit. Remember all the different pKa's, 3 o'clock, 7 o'clock, and 9 o'clock, 3.3, 7.7, and 9.5. pH less than 3.3 at 3 o'clock inactivates the ring by epimerization. 7 o'clock, you form insoluble salts. Fecam2, say it enough times it sounds like a word, Fecam2 and aluminum 3. And you also form magnesium, interactions with magnesium in the ribosome. 9 o'clock at pK3 at 9.5, you protonate the amine, you interact with a phosphate group in the ribosome, which is shown here. 3 important reactions that tetracyclines undergo include dehydration, epimerization, and cleavage. Remember, reactions 1 and 2, dehydration and epimerization, are not good don't happen with minocycline and doxycycline. Different resistance mechanisms. Mls drugs, Major League Sucks, Macrolide, Lincosamides, streptogramins, they all act at the 23S subunit of the 50S subunit of the ribosome at different parts of the exit tunnel. Bacteria all have resistance for Mls drugs through the gene, which creates an protein, which methylates adenosine to dimethyladenosine. And if you add methyl groups, you push the drugs out, they can't act anymore. Macrolides look for the lactone ring, this osamine group, which has the amine over here, so it's this osamine, and the cladinose ring in the bottom. And both these sugar groups lead to inhibition activity. Azithromycin and clarithromycin are made semisynthetically. Mechanism of action, already told you. Resistance, already told you. Lincosamides, look for the linking amide. So linking amide, the amide that's linking the left and the right side. Clindamycin has a chlorine group to increase lipophilicity and absorption. It has overlapping binding sites, but not identical binding sites. Clindamycin has 2 prodrugs, clindamycin phosphate and clindamycin palmitate. This increases the solubility and the lipophilicity, which increases the absorption of the drug. 2 streptogramins include dalfopristin and quinipristin in the 70-30 ratio to make Sinercid. Dalfopristin binds the beginning of the tunnel. Quinipristin binds deeper in the tunnel. Like dalfopristin is the beginning of the alphabet. Quinipristin is later in the alphabet, so deeper in the alphabet is quinipristin. Beginning of the alphabet is dalfopristin. Resistance mechanism. Oxazolidinones. Look for the oxazole ring. The oxazole ring. Oxazole ring. Same subunit, 23S subunit, but it binds to the A site. Remember, it binds to the A site. And resistance mechanism, don't feel like talking about it. If you have any feedback or other comments, remember to always put them at, let's do it in blue today, pollev.com/CHRISTIANRUI629. I always take feedback. I didn't get any constructive feedback last time, just some really funny ones. So yeah, feel free to leave feedback anytime. Thanks for watching.